So now, having done with the cyclic structures of glucose, what I'm going to do is, so what did I get after drawing all the cyclic structures? I got this particular structure which I've drawn at the bottom here on the left hand side. But now what I do is, I want my O, which is here, I want this O to come at this position here, and I want the numbering to, I was doing the numbering from here. So this was my first, this was my second. Now I want my numbering to start from here. So I want this as my first, and I want this my second, and so on and so forth. So what I'm gonna do about all this? I'm just gonna rotate this a little bit, this whole cyclic structure a little bit. What I do is now, I know my first carbon was here and the second one was here. So in this first one, having decided this as the first position, I take the OH on the top and the H at the bottom. Okay. Now I move on to the second carbon and I do the same, exact same thing. So I have H at the top and I have OH at the bottom. Also, at the third one, so I continue this till all the carbons are covered, and I've got at third, I've got OH on the top and H at the bottom. Then at fourth, I've got H at the top and OH at the bottom. And in the last one, I've got CH2OH at the top and I've got H at the bottom. Okay. Now we know that C1 here, the first carbon, the first cyclic carbon, was anomeric. Anomeric means it could change its configuration. The OH could go down. So now in this next one, what I'm going to do is I'm going to place this OH that I had placed here in the downside direction. So I will just put this OH over here and the rest of the structure is a copy paste. Okay. So I'm just drawing these two anomers. We had these anomers in the other structure of glucose as well. So here what am I actually doing? Just changing the position of oxygen and I'm shifting all the groups according to it. Now, why am I doing it? Because I want to see a little fact, and I want to state a little fact is that here if you see in this, let us call it A and let us call this as B. Okay. So in A, you can see that all the OH, see this OH, this OH, this OH, then I have OH, and I take this CH2OH group. They all are trans to each other. Okay, so all the groups here are trans to each other. But when I look at this one here, I have got this, I have got this, these two are trans, so is this, and so is this. But when I come to my last OH, I see that this is not in trans with this OH, but rather it is at this position. So what is the differentiating factor here? It is that here in A, all groups are trans. So all groups are trans to each other. And in B, I have got C1 is this and the rest are all trans. Okay. So this is the differentiating thing between these two A and B structures. Now what does that lead me to? I can now name them. So I'm going to name them. So where all the groups are trans, I call it the beta, and where all the groups are trans, leaving only the C1 atom as cis, I call this alpha form. So now I have got this as beta form and this as alpha form. Now what I'm gonna do now is I compare this with one particular structure that I have in mind, and that is of pyrin. So what is pyrin? If I draw a little rough figure here, pyrin actually looks something like this. So it is actually a six-membered cyclic ring and it has got two double bonds at this position, and I call this as pyrin. So this is pyrin. Now this is a six-membered chain. These two A and B are also six-membered and have also got an oxygen at this place as similarly as pyrin. So this new structure that we are forming now, these A and B structures are similar to pyrin. So now I can extend the name a little forward and I can now call this as beta D because it was D glucose and beta D glucopyranose. Okay, so now I've got a new name for this whole thing, and this A structure I'm calling it beta D glucopyranose. Also, I'm extending the name of the second one also, and now I'm calling it as alpha D glucopyranose. Alpha because of all the trans and one cis, and D because we have decided on the configuration because the OH was on the right hand side at the open structure in the last chiral carbon. Gluco because it is glucose of course, and pyranose because it is a little similar in structure with my pyrin ring. So I call this beta D glucose glucopyranose, and I call this alpha D glucopyranose. So I've got these two forms. So these two forms, this alpha D glucopyranose and this beta D glucopyranose, these both are actually in equilibrium with the open structures. Okay, so it is in equilibrium with the open structure of glucose. And these two, so I'm gonna write a little fact here that A and B, my A and B are actually anomers. Okay, so they are anomers, and that is because they differ in the placement of only one OH group at the C1 carbon atom. That is this carbon atom and this carbon atom. This OH placement is a little different. Okay, so I have learnt now that these two are anomers and their names alpha and beta. Now I want to see which of these two is the most stable one. Okay, so what I do next is I have this here, and now I can just quickly draw the structure of alpha and beta D glucopyranose. So on the left hand I'll draw the beta. I'll draw the beta D glucopyranose, and it looks something like, okay, so it has OH at top and H at bottom, referring just the previous figure that I drew before this. Okay, so I have OH and an H here. I've got an H and an OH here, and I've got a CH2OH and an H group over here. On the right hand side, I'm gonna draw my alpha D glucopyranose, and the only thing that was making it different from my beta D glucopyranose was the placement of OH. And at the first carbon here I've got my OH, which is cis to my second one. So that I complete now rest of the valencies. It is H, this is H2, and it looks exactly the same as the previous one in the rest of at the rest of the places. So I've got an H here, got an H, and I've got an OH here. So now if I want to compare the stability of these two, what I'm going to do is I'm going to bring them to the boat form. Okay, now in the boat form, what I'm going to do is I'm going to see whether all the groups lie at the equatorial plane or the axial plane, and wherever there are more equatorial, of course there'll be more stability, and therefore I'll declare that particular alpha or beta form as the more stable one. So what I'm going to do is I'm going to bring them now in the board form. So now I'm going to do the board form. Now what I'm going to do in the board form is that I see here that my O is placed, that this O I'm placing right at this place. So what I'm going to do is now is that I'm going to start from just the bottom, just area which is at the bottom of this O. And what I'm going to do is I'm going to place my OH now. So my OH, what I'm going to do is I'm going to place my OH at the equatorial position over here. Okay. Now I see in my beta D glucopyranose that the first carbon and the second carbon, the OH, are trans to each other. So if this is trans to each other, then of course this will also lie at the equatorial position, because if it was at axial, these two would have been at cis to each other, and I don't want that, because in beta D glucopyranose all the groups are at trans to each other. So the next the third one is also OH and it is at trans to the last one. So I've got OH at trans, and this falls also in the equatorial plane. Next up I have OH, and OH, my OH here also, it falls in equatorial position, because if it falls at the axial position, it is gonna be cis with my previous OH. The last I'm left with is CH2OH, which is actually on the fifth carbon over here. So if I look at this CH2OH, it is in trans with this OH, it is in trans. And now if I'm going to draw these two, what I'm going to do is I'm going to put my CH2OH at equatorial position. So this is also at equatorial position. So I've got my all the groups in the equatorial position in this particular beta D glucopyranose. Okay, so in beta D glucopyranose, I have got all of my OH at equatorial position. Now I come to the right hand side in the alpha D glucopyranose, and what I do is I'm gonna place my groups now. So here I have got OH at the downwards side, and therefore this OH is gonna be at axial position and not at equatorial. The next up I have OH, which is at cis to it, and if it is at cis, then of course it is going to come at equatorial and not the axial, because the axial lies at this direction and then they're going to be trans to each other. Okay, so now I have my next group. Now this OH and my this OH are trans to each other. And so I just repeat what I did in beta 2 glucose, and I place this at the equatorial position. Next OH, which is this one right here, is in trans position with that the previous OH, and therefore now I have got this also at equatorial position. The last I'm left with CH2OH, and therefore since it is also at trans to the previous OH that it is joined to, so now I have also got this at the equatorial position. So I have got all the groups that are in my glucose in at various positions. Okay. Now what I see is I observe this little fact that here all the groups are at equatorial position. So they all are at equatorial position. Also, we have discussed this one fact that I want to bring to light again, was that if I had my OH over here and it had lone pair, and I had my OH over here, so I had my OH and my O over here. So what I did was this lone pair and this hydrogen, they actually, this oxygen and hydrogen come into hydrogen bonding and makes it more stable. So here what happens is this particular beta D glucopyranose, because all the groups are at equatorial position, becomes more stable. So stability is in this order. So if I'm to write the stability order, what do I get? I get the beta form being more stable than the alpha one. Okay, so this was what I was looking for, was the stability order. So I can just write a concluding statement over here that I want that what did I do in this whole example that I was just putting forth was the beta form is more stable than alpha form because all substituents are present in or present at equatorial position. So this is what I concluded, that since all the groups are at equatorial position, automatically my beta form is greater stabilized than my alpha form. So the conclusion that I can draw is this one. Okay, my beta form is more stable than my alpha form, and I have proved why it is so, because in the boat structure I have got all the substituent present in the beta form at the equatorial position, and therefore making it more stable. So this is how I decide the stability order.